Welcome to the Explainer. Okay, if you're a stressed out student staring down the barrel of a massive midterm right now, take a deep breath. You are in exactly the right place. Today, we're doing a fast-paced, high-octane speed run covering the absolute most essential concepts from Units 3 and 4 of deep learning and neural networks. We're going to take all that complex, heavy lecture material, strip away the fluff, and focus strictly on what you actually need to know to understand the concepts and, most importantly, ace this exam.
Here's our game plan for today. We're going to hit deep learning basics, meet the CNN, break down the CNN architecture, look at the input and convolution stages, dive into pooling and fully connected layers, and then wrap the whole thing up with a final exam revision. Let's not waste any time.
All right, starting with Section 1, Deep Learning Basics, and the big paradigm shift.
Think about traditional machine learning for a second. It's incredibly tedious. Human experts literally have to manually step in and extract useful features from the data before training the model. But deep learning, it eliminates that limitation completely. It automatically learns features through its multiple layers of processing, kind of mimicking the human brain. No human hand-holding required. Now, listen up, because this is absolutely an exam-important concept. If you see a multiple-choice question asking about the main advantage of deep learning over traditional ML, you are looking for the words automatic feature extraction.
Moving right along to Section 2, let's meet the CNN, the absolute powerhouse of computer vision.
The primary applications of CNNs include things like face recognition, medical imaging, and object detection. So here is your very first core memory shortcut for the test. Whenever you see CNN on your paper, your brain needs to instantly scream images. Now, to ace the broader algorithm section, you've got to contrast this with the other architectures. If the exam asks about sequential data like text or time, that's an RNN. If it asks about fixing the vanishing gradient problem to handle long-term memory, that's an LSTM. Generating synthetic data, that's a GAN, where a generator and a discriminator actually compete against each other, and compressing then reconstructing data, that's an autoencoder. But remember, for images, CNNs rule.
Which brings us to Section 3, CNN architecture. This is our blueprint.
Think of a CNN like a giant, highly efficient factory pipeline. Raw data comes in on the left, it moves through convolutional layers, then pooling layers, gets flattened out into the fully connected layers, and finally hits the output layer. If you can just close your eyes and visualize this exact sequential flow, you've practically already passed the architecture portion of your midterm.
Let's zoom in on that pipeline in Section 4, the input and convolution layers. This is where we start the engine.
First up is the input layer, which receives our image data. But computers don't actually see pictures like we do, they just see matrices of pixel values. This is a prime spot for trick questions on the exam, so notice the distinction here. A grayscale image is represented as a two-dimensional matrix, but a color image? That's represented as a three-dimensional matrix because it has to account for the red, green, and blue, or RGB, color channels. So grayscale equals 2D, color equals 3D. Lock that in.
All right, now we hit the big one, the convolution layer. This is the absolute core component of a CNN, where the real magic happens. We take these small matrices, which are called filters or kernels, and we literally slide them across the input image. As they slide, and by the way, we measure that movement by a term called stride, and we often add padding to the borders to keep our data dimensions totally intact, they perform element-wise multiplication. This sliding mathematical action is exactly what extracts important image features and detects patterns like edges, shapes, and textures.
To summarize that whole mathematical operation into a super simple formula you can memorize, filters plus sliding element-wise multiplication across the image equals what we call feature maps. So, the feature map is just the output of the convolution layer. It's literally a map highlighting all the specific features that filter was looking for.
Now we need to clean up that data in Section 5, pooling and fully connected layers. Time to refine things.
So, what do pooling layers do? They reduce dimensions while preserving the really important features. Basically, they take those large feature maps we just made and shrink them down, which means compression. If we decide to keep only the absolute highest value in a region, that's called max pooling. But if we take the average of the values in that region, it's average pooling. Either way, it makes the entire network faster, lighter, and prevents it from just memorizing useless noise.
After we've convolved and pooled all our data, we eventually reach the fully connected layers. You can think of this as the final classification stage. The network takes all those refined two-dimensional feature maps, flattens them completely out into a single 1D list of numbers, and uses traditional neural connections to make the final prediction. Like, is it a dog or a cat? The fully connected layer makes the call. And to make that final decision, it uses mathematical functions. It uses softmax for multiple categories, or sigmoid if it's just a simple binary yes or no question.
Oh, and real quick before we leave the architecture, you've got to know about activation layers. These are components that introduce nonlinearity into a neural network, usually through functions like ReLU. Without them, our super deep, complex network would literally just be doing basic linear math. Now, once our network actually makes a prediction, we have to evaluate how good it is using performance metrics. This is exam important, so memorize this split. For regression tasks, where you're predicting continuous numbers, we use metrics like MAE, MSE, and RMSE. But for classification tasks, where you're predicting categories, we use accuracy, precision, recall, F1 score, and ROC-AUC.
All right, take a breath. We made it to Section 6. It's time for the final exam revision, the rapid-fire finish.
First things first, recite this step-by-step sequential flow of a CNN with me. Seriously, do it, because this is the ultimate multiple-choice exam hack. The data goes 1. Input layer, 2. Convolution layer, 3. Pooling layer, 4. Fully connected layer, and finally, 5. Output layer. Input, convolve, pool, fully connect, output. Memorize that sequence and you are golden.
Okay, let's rapid fire through our core memory shortcuts to cement this entire syllabus in your brain. When you see CNN, you think images. RNN equals sequences. LSTM equals long-term memory. GAN equals synthetic data generation. Autoencoder equals compress and reconstruct. For the architecture concepts, deep learning is automatic feature extraction. Filters extract features through sliding multiplication. Pooling reduces dimensions. And finally, for performance metrics, regression equals MAE, MSE, and RMSE. Classification equals accuracy, precision, recall, F1, and ROC-AUC.
Which brings us to our final thought. If traditional machine learning requires tedious manual extraction, are you ready to let deep learning automatically extract your path to an A+? You now have the blueprint, the definitions, and the critical memory shortcuts to absolutely crush Units 3 and 4 of your midterm. Best of luck on the exam, keep exploring the incredible world of artificial intelligence, and I'll catch you in the next explainer.